Because it's fun. All right, who wants to share something they learned in chapter 7? Let's try to get 3 responses.
Oh.
Lauren.
Scale factors.
Scale factors, good one. That was a big idea. Ratio, scale factor, proportions, all that. Yes.
Side, angle, side, similarity.
Side, angle, side, sim. Side, sim. Angle, sim. Walker.
I was just about to say sides.
Oh, I took yours. Sorry. Side, sim. Alejandro?
If you take a triangle and dilate it and line up all their angles, you can get to 1 point. That was in your notes.
What?
Oh, the center of dilation?
Yeah.
That you're talking about?
That was fun.
Cool. We didn't do any examples like that, but
I know,
I know what you're talking
I
about.
looked at it.
That's it's just very specific. I like it. Nice. Okay, as I mentioned, you guys, chapter 8 is the best. We study all about right triangles. There's so many cool, like, special relationships with right triangles. And we do a little trigonometry, which is awesome. Not till 8.4, but it's very fun, and I'm so excited. Okay, but first, I noticed this on your quiz, and obviously I haven't graded your test yet, but I noticed this on our quiz that some of us are still struggling with simplifying radicals. And I'm telling you right now, when you get to Algebra 2 next year, you're expected to know how to do this, because it's technically an Algebra 1 skill. And we do it a lot in Chapter 8, so we'll keep practicing it, but I want to kind of re-go over how we simplify radicals. The weird thing is I know some of you were taught 2 different ways. So I do think this is the easiest way to do it. And once you get to Algebra 2 in Chapter 6, we just finished this 2 weeks ago or something, you start to work with even higher roots, like cube roots and fourth roots and sixth roots. So you need to really understand how to do square roots in order to build on that concept to do higher roots in Algebra 2, okay? So this is important, is what I'm trying to say. I think the easiest way to simplify radicals is by looking at the radicand. Do you guys know what that word means?
Nope.
The number underneath the radical. So 80 would be the radicand here. The number underneath the radical, and you're trying to find factors of 80 that are perfect squares. All right? So I'm not going to do 8 times 10 because 8 and 10 are not perfect squares. I'm trying to break it up as a perfect square factor. Do you guys know which numbers are perfect squares? Let's create a list. 1 is technically a perfect square, but every number has a factor of 1, so we're going to ignore that one. What's my next smallest perfect square number? 4. Yep, 2 squared is 4. 4 is a perfect square. 9. Yep, you can keep writing these if you want. I'm not going to. 16 is a perfect square. 25. 36. What's the next one?
49.
49. 7 times 7 is 49. 64. 8 squared. 9 squared, 81. 10 squared? 100. 11 squared?
121.
12 squared?
144.
13 squared?
169.
All right, that's good for now. Good job. Okay. Obviously, this could go on for a while. I would say in this class, you're not going to get a whole lot higher than having to know what 13 squared is, but it's possible. So then what you do is you break up the radical into its perfect square factor and then whatever other factor it is, okay? And then you square root the perfect square and you leave the other one under the radical. And this is the same idea when you have other roots like cube roots and fourth roots, etc. All right, so let's try one as an example. 80. Now, what might pop into your head first is 4, which is good, but we want to find the biggest perfect square that's a factor of 80. There's one that's bigger.
16.
16? Do we agree? Is 16 going to 80?
Yes.
Okay. If you struggle a little bit with number sense or even mental math, you can just take your calculator, take the number 80. Don't actually use the radical button. Just do 80. Divide it by, and just start dividing it by some perfect squares. Now, obviously factors are always smaller than the number itself, so you would start You'd start your list about here. You'd only try ones that are smaller than 80. Accidentally erased my list here. Okay, so Matthew's right. 16 is the largest perfect square that goes into 80. So in your calculator, You do 80, you could try divide by 36. Oh, I get a decimal. That means 36 is not divisible, or 80 is not divisible by 36. 36 is not a factor. 80 divided by 16 is 5. So I'm breaking this up, and you can do this. This is a property of radicals that you talk about in Algebra 1, that the square root of 16 times the square root of 5, as long as they're both square roots, you can multiply them together. That's the square root of 80. So we're just kind of going backwards. Instead of multiplying these together, we're breaking it up, and that's what simplifying and factoring is. You just undo multiplication. All right, so here's my perfect square factor. So then you actually square root the perfect square. What's the square root of 16? 4. And that's what this radical symbol does. It unsquares the number, and then you leave root 5. Okay. Probably one of the last times you'll be taught that in your math career, because that's a skill that comes up a lot that we need to know how to do. Okay. My last class didn't remember this. I'll see if any of you guys do. Anybody know what an arithmetic mean is? Arithmetic mean. Alejandro?
Probably a mean.
What's a mean?
The middle, not middle, but it's the average.
The average, yep. Okay, so arithmetic in math means adding. So the arithmetic mean is we add the two numbers and we divide by 2. Yeah, find the mean or find the average. That's what I do to calculate your class averages, right? I add up all your test scores, divide by 21, however many of you were in this class. And what I'm really calculating is the arithmetic mean. So arithmetic mean of 9 and 4, I would just do 9 plus 4, which is 13. Divide that by 2, so 6.5 would be the arithmetic mean. It's the average of 9 and 4. What we're going to talk about is the geometric mean, because this is geometry. Get it? Okay, so the actual concept of a geometric mean is more used in statistics, and we're not going to really get into that. What you need to know is the geometric mean, and it kind of comes from a proportion. But what you need to know is that the geometric mean is the square root of the product of two numbers. Okay, so the arithmetic mean is you add them, divide by how many there is. The geometric mean, you square root the product of the two numbers. Okay, and again, conceptually what this means is something like we use to represent in statistics. We're going to put it into a triangle to show you how it's applied in geometry. But here, if they ask us what the geometric mean of 9 and 4 is, we take 9 times 4. Sometimes they use x. You can use x if you want to represent the geometric mean. We take 9 times 4, and we square root that product. So what's 9 times 4?
36.
Square root of 36? 6. 6 is the geometric mean of 9 and 4. Notice how that's not the average, right? That'd be the arithmetic mean. So geometric mean, what you need to know, square root of the product of two numbers. That's it. You can write that down, the wordage if you want. We'll do a couple examples here. Find the geometric mean of 12 and 15. Okay, so like I said, you can put x equals if you want. Geometric mean, I know that's the square root of the product of those two numbers. So I set it up just like that. Note here, we don't want decimal answers unless the two numbers given to us were decimals. So this is where our simplifying radical skills is going to come into play. First of all, I could do 12 times 15, which is 180. 180 is not a perfect square. If you take the square root of that in your calculator, you're going to get a decimal. We don't want decimals. Instead, we want to figure out what perfect square goes into 180, and not just any perfect square. What's the biggest perfect square that goes into 180? So again, if you struggle a little bit with factors and number sense, start with your calculator 180 and just start dividing it by perfect squares. Divide by 81. Ooh, no, that doesn't work. Divide by 64. No, 49. Da-da. 36 will tell you 5. 180 is the same as 36 times 5. What's the square root of 36? 6. I always write the perfect square factor first, too, because then it can just feed down into my final answer. I square root this number, leave the one that's not a perfect square. So 6 root 5 is a geometric mean of 12 and 15. Ooh, let's try one with radicals already in it. You ready for this, Malin? Okay. The geometric mean is the square root of the product of these two numbers. 3 root 6 times 5 root 6. Oh my gosh, radicals within radicals. Don't get freaked out. You can do this. Let's start with what we know how to do. I know how to do 3 times 5. That's 15. Okay, let me ask you this question. Write down on your paper what you think this is. Square root of 6 times the square root of 6. Write down really quick what you think the square root of 6 times the square root of 6 is. Don't say it out loud. Off to the side, not in here. Off to the side. What's this? I'll move it over here. Here's mine. Okay, any guesses? Tyson? 6? Any other guesses? You got 6 too? Anybody else get 6? Yes. 6 is right. 2 ways you can think of this. You could actually multiply them together. Right? Or you're really, I don't know if you would think of it this way, but 6 times 6 I could write like this, and then the square root just undoes the squaring. 6. All right, so 3 times 5 is 15. Square root of 6 times square root of 6 is 6. So I kind of took care of my double radical problem. 15 times 6 is 90. You guys can shout it out. What perfect square goes into 90? Pretty obvious one. 9. 9 times 10. So this geometric mean is 3 root 10. Okay. We're going to calculate geometric means within triangles in a minute. But there's some on your homework where it's just straight up practicing finding the geometric mean. No decimals unless the two numbers have decimals. Okay. Before we get into the geometric mean part, we first have to look at some triangles here, specifically within right triangles. As I mentioned, there's just so many cool things about right triangles. Here's one of them. If I have a big right triangle, so I'll do this in blue here, it's kind of upside down, but you see this triangle ACB, and my right angle's right here. What do we call this side? Hypotenuse. Good. Yep, hypotenuse is the side that's across from the 90-degree angle, okay? The hypotenuse. This theorem says if you draw an altitude, altitude is, you know what it is? From a vertex perpendicular to the opposite side. So if you draw it from the right angle to the hypotenuse, this altitude right here, it creates 3 similar triangles. This one, this triangle right here, will be similar to the big triangle. This little triangle right here, which is also a right triangle, see that right there, this one right here, will be similar to the red one and to the blue one. Okay? It's a little bit easier to see. Here they just kind of like carried down, but it's easier to see obviously when we have like numbers on it, and you can see that the sides are all proportional. They have like similar corresponding sides. So we'll look at one like that and later on. But what you need to know is that if we have an altitude that's to the hypotenuse, that it creates these three similar triangles. Okay, so we got to be careful in how we write this similarity statement because I need to keep all my corresponding sides in check. You guys know how I'm picky about that. All right, so this blue triangle, let's do this. Let's start at the right angle. So I'm actually going to start with C. Let's go C, up the shorter leg, B, down the hypotenuse. So CBA is similar to, all right, so the red triangle right here. I started at the right angle. I went up the shorter leg. Legs are like the other two sides that aren't hypotenuse of the right triangles. Legs, we call those legs. Up the leg, down the hypotenuse. So DCA. Obviously, there's other options you could do. You don't have to do it this way. You just have to be consistent. Which is similar to the green triangle. Starting at the right angle. Up the short leg, down the hypotenuse. DBC. All three of those triangles at that altitude essentially, well, the altitude splits it into two triangles. So those two triangles and the big triangle are all similar to each other. Okay, so let's try one example here. Write a similarity statement identifying the three similar triangles in the figure. So I'll outline my big one in blue. This is obviously a right triangle. It's just flipped upside down. Here's my altitude. So it splits it up into this right triangle and this little guy, which because this is a straight line, supplementary, whatever you want to think, that's also going to be a right angle. Okay, so let's write our similarity statement here. Triangle. Let's go in that same order. I like that. Let's start at the right angle. Let's go up the short leg, down the hypotenuse. Even if it's a little out of alphabetical order, let's do F, E, G is similar to, okay, so I started at my right angle. I went up the short leg, H, F, down the hypotenuse, H, F, G. Those will be my corresponding sides, which is similar to triangle. Start at the right angle, up the short leg, down the hypotenuse, H, E, F. Sometimes it helps students too if you want. You can like draw each triangle in the same orientation as the blue one. So like for example, they kind of did that, but they kept them the same, like they just carried them straight down. Like you could redraw this red triangle if you like flipped it over and kind of made it look upside down like the blue one. So picture that. That would F would come down here, F, H, G. And then it might be a little bit easier. You go, oh, F, E, G, H, F, G. If you wanted to do that. Same with like the green one. If you want to redraw it and flip that end up, you could do that. You don't have to. If you're okay with doing this, then that's fine. All right, here's the three big theorems. Well, two, I should say. Two big theorems. The third one we just learned. And we're going to tie in the geometric mean. All right, so I'm going to do a little like proof over here. It's really short. A little proof of this theorem. So here's my big right triangle. I'll use my colors again. And if I drop an altitude from the right angle, I know it's going to split this up into three similar triangles, right? So we just talked about. Okay. So looking at my green triangle, X is one of the legs, and it's like the shorter leg, right? Everybody see that? X. Looking at my red triangle, what side would correspond to X? AKA, in my red triangle, which leg is like the shorter leg? H. X corresponds to H. All right, I'm going to set up a little proportion here. We know this because they're similar. All right, back to the green triangle. H, which is my longer leg, corresponds to, in my red triangle, y, which is my longer leg. Okay, those are like the similar corresponding sides. If I were to cross multiply this, watch what happens. I would do h times h equals x times y. How would I solve this for h? This little equation. Ben? Square root, yep. H is the square root of x times y, the square root of the product of two numbers, which is also called the geometric mean. Okay, here's the theorem. The altitude, specifically the one that's to the hypotenuse, is the geometric mean between the lengths of the two segments that it splits the hypotenuse into. So x and y. You guys see here how the altitude is just the geometric mean, the square root of the product of those two segments. Okay? The altitude is the geometric mean of the two segments that it splits the hypotenuse into. This comes from this proportion. What I'm telling you right now is if you know this theorem and you essentially kind of like, I don't want to say memorize, but kind of memorize this, that the geometric mean of the two segments that the hypotenuse split into is the length of the altitude, is going to be way quicker than setting up a proportion every time and like trying to solve for h, the altitude, okay? All right, here's my next one. I'll prove it to you first. I have another triangle. You won't ever have to prove it to me, but I like my proofs, so get used to it. I have an altitude here to my hypotenuse, splits it up into two triangles, which are similar to each other and the big triangle. All right, now instead of looking at the length of the altitude, we're going to look at the length of the legs. This one's called the geometric mean leg theorem. This one, geometric mean altitude theorem. Okay, so again, we're going to set up a proportion here with similar triangles. So we're actually going to do the big triangle. The length of this hypotenuse they're calling C. Okay? C. Which one do I want to do first? Let's do the green one. C corresponds to the hypotenuse of my big triangle, and in my green triangle, the hypotenuse is B. Okay, back to the big triangle. B, which is my shorter leg of that big right triangle, corresponds to, in my green triangle, X, which is the shorter leg in that green triangle. All right, similar idea here. Watch what happens. I cross multiply. I get B squared equals C times X. Actually, I'm going to write it as X times C. I think that's how it is in your textbook. X times C. Square root both sides. That leg is the geometric mean of this little segment X times the whole hypotenuse length. Okay, one more little proof for A. Very similar, same exact idea. So now looking at my red triangle, the hypotenuse C of the big triangle corresponds to A in my red triangle. Oops, A goes up here. A. A in my blue triangle, which is the longer leg, corresponds to Y in my red triangle. Cross multiply, get A squared equals Y times C. A is the geometric mean of this little segment and the hypotenuse of the whole triangle. So here's what you need to know in short. The altitude is the geometric mean of the two segments that it splits the hypotenuse into. Each leg is the geometric mean of the entire hypotenuse and the segment that's adjacent or that makes up or touches that side, that leg. Okay, let's try an example. All right, so here I have to find the altitude E, and I have to find both the legs to this big right triangle. So again, we could set up a proportion with the similar triangles and all that jazz, but it'd be way shorter to use this theorem, especially because, look at my altitude here. I know what it's splitting the hypotenuse into. It's splitting the hypotenuse into a segment of 6 and 24. That's what they're showing me right there. So for that first theorem we talked about, the altitude theorem, I know the altitude is the geometric mean of the two segments that it splits the hypotenuse into. And I know geometric mean is the square root of the product of the numbers. 6 times 24. Right now I'm going to start finding E. 6 times 24 is 144. Perfect square, E is 12. All right, there's my altitude theorem because E was an altitude. Now to find each leg, I'm going to use the leg geometric mean theorem. Let's do C first. It doesn't matter. I know the leg, according to this theorem we just talked about, the leg is the same length as the geometric mean of the entire hypotenuse, which, if this segment's 6 and this segment's 24, what's the whole hypotenuse? 30. So it's the geometric mean of the entire hypotenuse and the segment that it is adjacent to or that touches it, so 24. We got a huge number here, 720. Woofda. So when you're simplifying this radical, because 720 is not a perfect square, start big. Look for big perfect squares that go into 720 and 144 does. It's 144 times 5. Square root of 144 is 12. Root 5. That would be the length of C. Again, we're going to practice simplifying radicals. There is stuff. Drawing. Okay, other leg, D. The leg is the geometric mean of the entire hypotenuse, 30, and the segment that touches that leg, 6. That's 180. You might be thinking 9 times 20, but 20 has another perfect square factor, so that means there's a bigger perfect square. It's 36 and 5. So 6 root 5. Great, so much practice with radicals. Isn't that awesome? Okay. That was a pretty classic example of showing you each theorem with applied to numbers here. Let's try one that's a little bit more challenging. So we're going to find X, Y, and Z. Here's my big right triangle, and this should be drawn in here. This right angle should be, go ahead, draw that in. They're showing me this right triangle. The weird thing about this one is I actually know what my altitude is. My altitude is 12. And I know one of the little segments that the hypotenuse is split into is 9, but I don't know the other segment. And then they also want me to find the length of each leg. But in order to find the length of each leg, since it's the geometric mean of the entire hypotenuse and the side that it is adjacent to, I first need to find X. Because I don't know what the hypotenuse is here. Oh no. Okay. So we're still going to use our little geometric mean formula, if you will. But you'll notice that my variable or my unknown is just going to be in a different spot. Okay, so what I mean by that is I still know that my altitude, which is 12, is the geometric mean of the two segments that it splits the hypotenuse into. So geometric means the square root of their product, so 9 times x we're going to write as 9x. We know the length is 12, so this just creates an equation where my x is stuck underneath this square root. Have I ever told you guys, my equations are like onions thing. That's what my other class said too. I feel like I say this all the time, but maybe not in geometry. Equations are just like onions, not because they make you want to cry, but because there's really just a bunch of, you guys, that was a funny joke. Come on. But because there's just a bunch of layers around your variable. So when I look at this equation, I see 2 layers on my variable. I see this times by 9, and I see this square root. How to get rid of them is by doing inverse operations. So how do I get rid of multiplying by 9? I divide by 9. But I can't do that yet because it's stuck underneath the square root. Ideas. Ben.
You can square it and then square the other side.
Square both sides. Squaring is the inverse operation, or it undoes the square root. It gets rid of that layer. But I like what you said. As long as we do it to both sides. Don't tell me that 12 squared is 24. 12 times 12 is 144. And then we can get rid of the 9 by dividing by 9. So I think that's 16. Okay. Now we know x is 16, which makes my entire hypotenuse what? 16 plus 9? 25. Thank you. 25. Now we can find the legs. I'll start with y. The legs are the geometric mean of the entire hypotenuse, which is 25, and the side that's adjacent or that touches that leg, so 16. Now, a couple ways you could simplify this. It's already broken up as perfect squares for you. So you could square root 25, which is 5, and square root 16, which is 4, and then do 5 times 4, and you get 20. Or if you don't recognize that, that's okay. You can actually times those numbers. You get 400. Square root of 400 is 20. Whatever makes more sense to you with the radicals. All right, now I got to find z. Z is a geometric mean of the entire hypotenuse, which is 25, times the side that it touches. Very similar setup here with perfect squares. You can either multiply them, which is 225. That's 15. Or you could square root 25 and square root 9. 5 times 3 is also 15. Yes, sir?
I could usually Python.
We haven't learned, that's a next lesson. We haven't learned Pythag yet. But we could, because it's a right triangle. Yeah. That's what, don't worry guys. That's what we're going to do on the first day back from spring break. So if that gets you excited to come back, I'll be here.
I'm so excited.
Right? Okay. Let's try a little harder algebra 1, because you guys seem a little bored. Find t. So I have my big right triangle right here. My altitude to the hypotenuse is 12. This segment's 24. This segment is t plus 1. So you could probably like guess and check until you find one that works. But you could also do this algebraically. We know the altitude is the geometric mean of the 2 segments that it splits the hypotenuse up to. So geometric mean is the square root of their product. Just like that. All right. I would first square both sides to get rid of that radical. You could distribute the 24. That's probably what most of you would do. Or you could just take off the layer of 24 by dividing by 24. And then you just have to move over the 1. We could also go from here. We'd subtract the 24. Divide by 24. That gives me 5. Okay, the last one's the best one. Save the best for last. Kind of a not very high quality screenshot photo here, but I took it from like a real life problem one in your textbook. The weird thing about this one is I know all the sides of the big right triangle. I know the legs, I know the hypotenuse. I don't know the altitude, and I don't know the lengths that the altitude splits that hypotenuse into. I'm like, is it like 2 and 5? Is it 3 and 4? I don't know for sure. And I don't know what the altitude is either. But I do know the length of each leg. So what I'm going to do, and I know the whole hypotenuse is 7. I'm going to call this, I want to call it X. I'll call it Y. Y. Actually, I'm going to call it A. I'm going to call it A, sorry. A. So I could set up my geometric mean for the legs, that the leg is the geometric mean of the entire hypotenuse, which is 7, and that little segment, which I called A, that's adjacent to that leg. I could figure out what A is by squaring both sides. .6 squared is 21.16. So here's an instance where decimals are okay because my original numbers were in decimals and we're talking about feet, so this is fine. Divide by 7. So I got A to be, and it's a pretty long number, so I'm just going to round it. That's why I'm using this approximating sign. I'm just going to go 3.02. All right, how could we find this length? It's called B. We could do the same thing, easier way. Yeah, we know the whole thing's 7. All right, so B is going to be approximate. I'm doing that again because I rounded this number. It's going to be 7 minus A. So B is going to be somewhere around 3.98. Okay, now that we know these two little segments, now we can find the altitude. The altitude is the geometric mean.
May I have your attention for a few
Oh.
end-of-the-day announcements?
Sure.
Following students, please stop in the office today at the end of the day. John King, Caitlin Schnitzler, Ashton Street, Olivia Horsfall. Again, John King, Caitlin Schnitzler, Ashton Street, Olivia Horsfall, please stop in the office.
He sounds sick.
Also, there are several lost and found items on the front
Sounds
side as you
nasally.
leave the building today. Please take a look at those things. They will be discarded tomorrow if not taken. Again, please take a look at the lost and found. Any high school students bringing a gift to the prom dance on the 9th, reminded that you need to get a dance form from the front foyer. Again, that's an out-of-town guest. Must be a high school student. That form must be returned to the office by Wednesday, April 6th. Again, that's a green form on the table in the front foyer. Bringing a guest to prom. Thank you.
Okay, so lastly, to find the altitude, it's just the geometric mean of those two segments we found. Decimals are fine, so I just rounded it to 2 decimals. Okay, wasn't that fun?
Yeah, sure.